Hi, Physics One. This is Mr. Janowski. This is the second part of the chapter 6-7 slides. So, the do now questions. What is the single most important thing you will learn in Physics 1? Newton's second law of motion, F equals ma. I promise you that's the most important thing I will teach you in Physics 1. Or even if you take Physics 2, this is still the most important thing I will have taught you over 2 years. So, question 2, if La Pulga Atomica, aka Leo Messi, kicks a bowling ball and a football, and the bowling ball has 16 times the mass of the football, well, certainly the football's motion is going to change more. It's going to accelerate more. But how much more will the football accelerate than the bowling ball? It will accelerate 16 times as much, because if F is equal to ma, well, then A is equal to F over m. If the F's are the same, but one of them has 16 times the mass, then that thing, the bowling ball, will have 1/16th the acceleration, which is the same thing as saying the football will have 16 times the acceleration. And now 3. If I were to stand on a bathroom scale, it would read my weight. If I were to suddenly crouch down, how would the needle on the scale respond? So this is an old-fashioned analog kind of bathroom scale. If I'm just standing there still, it reads my weight, and then suddenly I crouch down. So does the needle go A, to lower numbers first, B, to higher numbers first, or C, does it not change? Does it not move at all since my weight hasn't changed? So here we are. This is what's going to happen. This is my demonstration. And yeah, we'll watch. It's in slow motion, by the way. So it started at 200, and then as I begin to crouch down, it goes to the lower numbers first. After this, it's going to bounce around, and at the end of the video, it's on the higher numbers first. I'm sorry, it's on the higher numbers at the end. But the important idea is, what does it do first? And the first thing it does is it goes to lower numbers. I do not weigh 175. That would be nice, but it ain't the case. So then it goes through the end. So yes, our answer is it will move to lower numbers first. And then the flip of this, if I start crouch down and then pop up, what's it going to do? So I'm starting crouch down. As I begin to pop up, it shoots up to the higher numbers. So in that situation, it goes to the higher numbers first. Now, this was surprising. Well, the first part was surprising. More people thought in the crouching down situation that it would go to higher numbers first, when in fact it does go to the lower numbers first. After that, most people figured out, okay, well, I was wrong about that one, but now I see how this works, even if I don't understand how it works. So they got this one right. So yeah, let's see how this actually works. So a couple things to remember today. One is that mass is not weight. Mass is a measure of inertia. It has units of kilograms, kg, and mass is a scalar. Weight, on the other hand, is a force. It has units of newtons, and it is a vector because it's a force. Forces are vectors. They have direction. So astronauts experience weightlessness, but they never experience masslessness. That's not a thing. That can't happen. So in this picture, we've got a bunch of different astronauts floating around on the International Space Station. Everything you see in this picture is weightless. Don't worry exactly how that works. I'll tell you that later in the year, how orbit leads to weightlessness. But everything in this picture is weightless. Now, if you notice this astronaut, she's pushing on this apple. The apple is not massless. She's putting a force on it, and so the apple is going to begin to accelerate because it still has its mass. So Newton's second law still applies. If she were to put that same amount of force that she is now putting on the apple onto this dude over here, he would also accelerate, but he wouldn't accelerate as much because he has much more mass, and that's Newton's second law. Anyhow, key idea, keep these ideas separate in your head. Mass and weight are not the same thing. So mass is m and weight is F sub g. So here's your formula for weight. F sub g is equal to m times g. So your weight is related to your mass, of course, but it's not the same thing. So F sub g is equal to mg, where g is positive 9.8 meters per second squared if you're near the surface of the Earth. So I have it in bold that we're going to start using positive 9.8 meters per second squared for g, which may be a little annoying because in the last two chapters we were using the negative 9.8 meters per second squared because gravity goes down. Well, gravity still goes down, but we will handle the downwardness of gravity differently in this chapter. So key ideas here, F sub g equals mg. That is weight. And little g is now positive 9.8 meters per second squared. The other thing we need to think about today is normal force F sub n. So anytime you have two objects in contact with each other, they exert a normal force on each other. So anytime two things are touching, there's a normal force. Normal in this context means perpendicular. So here's an important idea. Technically, scales don't read weight. They often read weight. If you're doing it right, it's going to read your weight, but a scale doesn't always read your weight. What the scale always reads is the normal force that it's exerting on the object that is resting on it. That is what a scale actually reads. Scales read normal force. Keep that in mind. So sometimes this number is going to be different than the object's weight. So moving on, here is Dr. File's four-step strategy for force problems TM. Now, Dr. File is a physics professor at West Chester University. That's where I got my teaching certification. And from working in the tutoring office, I had many students of Dr. File. I never actually had Dr. File for a class, but I had many students of Dr. File who needed tutoring in physics. And through those students, I learned Dr. File's strategy for force problems TM. So this is what it is. It's a wonderful strategy. And of course, my four-step strategy is going to have 6 steps because my four-step strategy begins with step and ends with step So here's how it goes. Any problem you get in physics, do a step first. Just make sure you understand what are we looking for, what units to be expected to have. After that, you do the sketch. So all year long, step 1 is sketch. Sketch tells the story. It includes masses, accelerations, velocities, coefficients of friction. You don't know what that is yet. Spring constants. You don't know what that is yet. Etc. All kinds of things. These are part of the story of what's happening, so you make a sketch. Step 2 in a force problem is the free body diagram. So this is different than step 2 in a kinematics problem, which is variable bank. In a force problem, step 2 is free body diagram. Now, the free body diagram comes from the sketch. You're going to turn the object into a box, and the only thing you attach to the box are forces. So the free body diagram is a kind of sketch, but it's a special kind of sketch, and there are rules. Whatever the thing you drew in your step 1 sketch, well, that thing is now a box. Just draw a square box. And the only thing we are going to attach to this box are forces. So we're leaving out everything else. So step 3 is the most important thing you will learn in physics all year, F equals ma, Newton's second law, only we're going to write it a little bit differently now. We're going to be more precise. We're going to write sigma F, meaning sum of the forces, and we're going to put a hat, that's a vector hat, on top of the F. So in a step 3 of a force problem, your vectors were hats. So we have sigma F with a hat is equal to ma with a hat. A is a vector, so A also gets a hat. M is a scalar. Scalars don't wear hats. So what we're going to do is we're going to build the left side of the equation using the forces in your free body diagram. I'll show you how that works with an example in a second. So at this stage, everything, all of your forces will be adding together, and they will all be wearing vector hats. So that's what's happening on the left side of the equal sign. On the right side of the equal sign, just remember that acceleration is a vector, so it also wears a hat. Step 4 is the math. In the math, the first thing you will do is take the hats off of your vectors and put in signs, plus or minus, to represent which way the thing is going. If the thing is going up, it gets a plus. If it's going down, it gets a minus. If it's going to the right, it gets a plus. If it's going to the left, it gets a minus. So that is the first part of math. Take the hats off, put in the signs. After that, the math is algebra. Solve for the thing you're trying to solve for, put in the numbers, get your answer. And then, of course, you draw a box around your answer, and then you do your step. Did I solve for the right thing? Did I give it the right units? Is this a reasonable number for this kind of thing? So we'll do an example here. So we've got a man with a mass of 82 kilograms standing on a bathroom scale in an elevator, which sounds very weird and contrived, but just go with it. That's how you learn the physics. The man on the scale and the elevator thing is it's a classic physics 1 problem. So this elevator is accelerating upwards at 3.2 meters per second squared. Notice we don't know if it's going upwards. I'll leave it at that. We don't know its velocity. We do know its acceleration. It is accelerating upwards. Whether it's beginning to accelerating upwards, but it's not moving yet, we don't know. It could be going down with downwards velocity, but accelerating upwards. I'm going too far in depth in this. Anyhow, the elevator is accelerating upwards at 3.2 meters per second squared. So what does the scale read in newtons? So step, what are we looking for? What does the scale read? Remember that scales read normal force. So we're looking for F sub n, normal force, is equal to question mark newtons. The next thing we do is step 1. Step 1 is always a sketch. So here is our sketch. It tells the story. We've got a man with a mass of 82 kilograms standing on a scale. So here's the scale. He's in an elevator, and the elevator is accelerating upwards at 3.2 meters per second squared. So that is our sketch. Step 2 in Dr. File's 4-step strategy for force problems TM is the free body diagram. So the man in this picture is now the box. He's now the blue square in this picture. And to this box, we only attach forces. We're leaving out the acceleration. We're leaving out the mass. We're only attaching the forces. So what forces are acting on this man? Well, he's got weight. He's near the surface of the Earth. And his weight is going to be equal to F sub g is equal to mg. And if we look at this picture, well, he's in contact with the scale. Therefore, the scale must be putting a normal force upwards on him. So we have a normal force going up. And that's it. Only forces in the free body diagram. Then we go on to Newton's second law. Sigma F with a hat is equal to ma with a hat. So A, build the left side of your equation using the forces in your free body diagram. So what that means is look back at your free body diagram, grab all of your forces, put hats on them, and plus them together. So our two forces are F sub n and F sub g. So over here, we have F sub n plus F sub g. I should have started with this. Please, when you're doing this, the first thing you should write down is this. Sigma F with a hat is equal to ma with a hat. Start with that. After that, build the left side, meaning turn sigma F with a hat into the sum of your forces wearing hats. And the right side is still ma, and a is still wearing a hat. In step 3, your vectors wear hats. So step 4 is take the hats off and put in the signs. So if we go back to this image here, free body diagram, we see that F sub n is going up, so that gets a plus sign, and F sub g is going down, so that gets a minus sign. So plus, the plus is implied, F sub n minus F sub g. And also, it's a subtle thing, but in this case, the elevator was accelerating upwards. So when we take the hat off of A in this problem, it gets a positive. So that gets us to there. Now remember, we're trying to solve for F sub n, so I add F sub g to both sides. So I have that. And remember, the other thing we learned today is that F sub g is actually equal to mg. So I'm going from this second line down to the third one, I am replacing F sub g with mg. After that, I've got as far as I can with the letters. I have to put in the numbers. I put in all of the numbers. I do the math. I get this plus this. I add them together, and I get 1066 newtons. And then I do step, well, I solved for the right thing. I gave it the right units. Is 1066 a reasonable number of newtons? That one's trickier because we don't deal with newtons every day, and you have no day-to-day experience with, what a normal number of newtons is. After you do enough physics problems, eventually you'll learn, yeah, that's a reasonable number of newtons. 1066 newtons. So yes, it gets a check. Now, I made a bit of a mistake about this too. When I wrote this problem, I had no intention to come up with the answer 1066 newtons. But when it worked out, I automatically thought of what I always think of when I hear 1066, which is the Battle of Hastings. 1066 was a very memorable historical year, the Battle of Hastings. That's when William the Conqueror, a Norman, meaning basically a French guy whose family used to be Vikings living in northern France, invaded England, and he beat Harold Godwinson, who was an Anglo-Saxon, the Anglo-Saxon king. Basically, he was an English guy whose ancestors used to be Vikings as well. So yeah, anyhow, 1066, William the Conqueror beat Harold Godwinson at the Battle of Hastings, and that's how William became William the Conqueror, which obviously has nothing to do with physics, but 1066, I can't hear that number and not think Battle of Hastings. So after that, we did this one. This was the first homework problem in homework 2, I believe. We did that one as a we do. And that was it. So we learned Dr. File's 4-step strategy for force problems, and hopefully you found that helpful.